So far for linear correlation, we have calculated the statistic R, talked about it being, close to 1 or -1 and having, strong linear correlation, either negative or positive. We need to have a statistical mathematical way to determine if that statistic R indicates that there is linear correlation or not. So in section 12.4, we look at a hypothesis test for linear correlation. So if we think back to hypothesis tests that we've done before, it always revolves around a hypothesis test about a population parameter. So we looked at hypothesis tests for population mean, mu, and population proportion, p. So the parameter is, we use the Greek letter rho. So it actually looks kind of like a p. It's that, and that's how you say it is rho. And rho, that's that true correlation coefficient that's being estimated by the statistic R, which is based on the sample data values. So the sample statistic R estimates the population parameter rho, just like X bar estimates mu, and just like P prime estimates P, the population proportion. So just like other hypothesis tests, there's going to be 4 steps. The first step, stating the null and alternative hypotheses, they're always going to be the same. So the null is, in words, that there is no linear correlation, and it looks like rho equal to 0. So if you remember, if we've got a correlation coefficient that's equal to 0, we say that there's no linear correlation. So the null is that rho is equal to 0. In other words, there's no linear correlation. And then the alternate is that there is linear correlation, and that would be the case as if rho is not equal to 0. The test statistic in step 2 is given there. It's going to be a t-value. All right, we take r, that correlation coefficient, and multiply it by the square root of n times 2, sample size minus 2, and then that's divided by the square root of 1 minus r squared. We find the p-value from the t-distribution. It's a two-tailed test, and the degrees of freedom are n minus 2. So that's a little bit different than what we've looked at before. So instead of n minus 1, we have n minus 2. And that's because we've got x values and y values. So accounting for both of those, the degrees of freedom, we take 2 off the sample size. And then the conclusion is based on the same rule. We're going to reject the null if the p-value is less than the significance level. And what that means then is that x and y are linearly correlated. So if we reject the null, right, which is that there is no linear correlation, if we reject that, that means that they are linearly correlated. And then if the p-value is greater than the significance level, we do not reject the null. So we don't reject that there is no linear correlation. So that means that x and y, the two variables, are not linearly correlated. So let's run through some examples. Let's say we've got a R value of 0.85, and we're assuming that we've got sample size of 15 here. If we calculate the test statistic, I'm going to take that 0.85, multiply it by 15 minus 2, or square root of 15 minus 2, so the square root of 13. And then divide that by the square root of 1 minus 0.85 squared. And that gives us a t-value, a test statistic of 5.818 if we round to 3 decimal places. Okay, so we go to the online tool to find the t-value. All right, we got to remember we want test statistic. We want degrees of freedom of 13. We're subtracting 2 from the sample size. And we want a two-tailed test. So we picked the option with 2 tails. And that gives a p-value, a really small p-value of 0.0001. Using that, that p-value is less than any of the significance levels that we might use. 0.01, 0.05, or 0.1. Okay, so that means that we will reject the null. And now we have to determine, does this R value represent correlation between the two variables x and y that this is about or not? Well, because we reject the null, that there is no linear correlation, we can conclude that they are linearly correlated. Okay, so for our value of 0.85 and sample size of 15, right, we are going to conclude that there is linear correlation. The correlation coefficient, and kind of just subjectively. Okay, so let's look at another one. If we've got an R value of negative 0.02, first thing we want to do is calculate the test statistic. So we take that negative 0.02, calculating the test statistic. We take that 0.96, multiply it by our sample size. For this example was 6, so we're going to take the square root of 4. All right, divide that by 1 minus 0.96 squared. That gives us a test statistic of 6.857. So I'm sure you're seeing the pattern that when we have a really high, large test statistic, t-value, that's going to give us a low, small p-value. Yeah, in this case, if we look that up, we get the p-value of 0.0024. So that means that we are going to reject the null hypothesis, and we are going to conclude that there is linear correlation between hours practiced and points scored. We have another example from last time about the sparrowhawk population in 13 different colonies. We looked at the independent variable, which was the percent that were returning sparrowhawks, and the dependent variable, which was the percent of the new sparrowhawks coming to the colony. And we came up with an R value of negative 0.75, and the sample size was 13. All right, so let's do the hypothesis test here to determine whether we have linear correlation. So calculate the test statistic. Take negative 0.75 times the square root of 13 minus 2, so 11, divided by the square root of 1 minus negative 0.75 squared. That results in a t-value of negative 3.761. So looking at the p-value, you get a value of 0.0031. Okay, conclusion, because that's less than any of the significance levels, we are going to reject the null, which is that rho is equal to 0. And we can conclude that there is linear correlation between the percent of returning hawks and percent of new hawks in these colonies.